Welcome back to another lesson with me, Mr. Wong. Today we're going to be looking at another physics question. This time it's related to orbital periods and speeds. This is from 2009, but it will help you understand Module 5 Inquiry Question 3. We go to question 19 and we have a satellite that is propelled from orbit 1 to orbit 2. So we have a little transfer in motion there. Orbit 2 has a radius of 20,000 kilometers. What is the satellite's speed in this orbit? Now, in order to solve this problem, you do need to know the formula of orbital velocity. You can try and derive it, or if you remember, this is the formula we're dealing with. If you're not sure how to derive it, there is another video on that from before, so please have a look at that. If I look at my formula sheet, I already know the value of capital G, so it's 6.6 times 10 to the power of negative 11 multiplied by the mass of the Earth, and we have the radius. Now, the radius that we need to calculate, besides this particular length here, which is 20,000 kilometers, which if we need to convert would be 20,000 times 10 to the power 3 meters. We also need to factor in this radius here. So the length of the center of our planet towards the surface. And on my data sheet, that is 6.371 times 10 to the power of 6. So what we need to do is add the radius of the Earth plus the radius of its orbit and put it in one formula like so. The value I get is, let's see, 3,463.01148 meters per second. If we look at the significant figures that we should round it off by, you can see 2 is the smallest number, so we round it off to the smallest significant figures of 2, so it'd be roughly 3,500 meters per second. And that solves us with that problem there. If we move on to question B, it says the radius of orbit 2 is 4 times that of orbit 1. What is the ratio of the new orbital period to the original period? Let's use a different color to highlight the scenario. So orbit B, let me just scribble these out so we have a new diagram to see. So from this point, let's see, to here, that is 4r, and we can imagine from this distance to this distance here is 1r. We want to find the time comparison of the two. So we can call this T1, we can call this T2, or however you like. In this problem, we are going to apply Kepler's third law of planetary motion. We're going to apply r cubed over t squared equals to r cubed over t squared. We're going to name the r over here as 1 and then this r as 2. What we know is if we have an object rotating around the same celestial object, the constant r cubed t squared will be the same. They might not have the same radius, they might not have the same period, but when we calculate the constant for it, they will be the same, so long as it's orbiting the same object. So we are looking at a ratio between the orbital periods of the original and the new orbit. So what we can do is we can reformulate our formula around. So we have T2 over here, T1 down here, and R2 over here, and R1 down here. We can substitute. So I know that we can say R2 is a value of equivalent to 4. So it could be said that it's 4 cubed over R1, which is just 1. If I then move the square root, or the square, and square root both sides, I get a value of 8. So what that implies is the new orbit is 8 times longer. The new orbital period is 8 times longer than the original period. And that's how you solve the problem. So you can see question 1 was a substitution problem, and then question 2 was about using ratios to develop and derive some relationships. It's a lovely question, and it tests you on a variety of skills. If you found this video useful in explaining these concepts, like and subscribe if you hasn't done so already, and I will see you next time. Take care.